So this is the next chapter. So what we're going to do here is really switch to, if I propose a certain model and I want to fit this model to given data that are potentially subject to censoring and truncation, then how should I do this, right? Because the considerations that we made up to this point, like this Kaplan-Meier, like the histogram in the previous chapter, etc., those were purely visualizations of the empirical data. And now we want to switch to calibrating the models that we talked about in the previous chapters, actually calibrating them to data, right? And we're going to do that, first of all, with a tool that is called frequentist estimation and techniques that fit within this framework. So that's chapter 13. So a recap from chapter 11 is, besides this dataset D2 that I talked about, we also have a few other datasets. This is dataset A, where I've got the number of accidents by a single driver or by a driver in a single year. I've got the results for 94,000 and so on drivers. So I know how many of them report 0 accidents, how many report 1 accident, etc. So one question here could be, would you model this data rather with the Poisson or with the negative binomial distribution? Could be just one question. And can you then calibrate the Poisson distribution to the given data set over here? That would be one question we try to answer in this chapter. If we look at dataset B, dataset B was about the amounts paid on a workers' compensation, medical benefits product. Payments are here the full amount of the loss, so that's important. That means that there is no right censoring, left truncation in the original setup of dataset B, right? Because it says it's the complete loss. And then we've got a random sample of 20 payments printed over here. So here a question could be, should I model this with a Pareto? Should I model this dataset with a gamma distribution, and so on, okay? And then dataset C is about payments on 227 claims from a general liability insurance policy. And here the peculiar thing is that you only have a certain range of values, right? And that you can only say, okay, I've got that number of payments within this specific range of payments. So you do not know the individual payments themselves. You only know within a certain interval how many payments did I observe over there. So these are grouped data. And here again, could we model, could we calibrate a parametric distribution on this given data set, and how should we do that? All right. So that's the idea for this session. So of course, if we want to model one of these data sets with a parametric model, think Poisson, think Gamma, think Pareto, etc., then we should assign certain values to the parameters in these distributions. So what we're going to do is we're going to explain moment estimation and we're going to explain maximum likelihood estimation. And sometimes we want to combine these two. Because, for example, one application that I have in mind is if you want to calibrate, let's say, a 4 or 5 parameter distribution like the BER or the GB2 or something. If you want to calibrate that to a given data set, you'll need clever initializations of your parameter values, often obtained then via moment estimation. So then the moment estimation could be used as a clever initialization of your numerical routine to fit or to do the numerical optimization of your likelihoods. We'll see that later. So first of all, a word about this method of moments approach. So what we're going to do here is we're going to assume that all our n observations are from a given parametric distribution, which we're going to denote here with F for CDF, could also be small f for PDF. So we're going to denote it, F is our distribution, and vector theta is the vector with the unknown parameters in this distribution. So if it's a Poisson, there will be a single unknown parameter theta. If it's a gamma, there will be a vector of 2 unknown parameters, and so on and so forth. Yeah. So in general terms, you could say there are p parameters which I need to calibrate on my data set in order to be able to work with this distribution. And what I'm going to do now is I'm going to look at the kth raw moment. And I'm going to look at the empirical estimate of the Kate moment for a sample of n observations. So let's first look at the empirical estimate of the Kate raw moment. So what you're going to do then is you're going to look at your observations, your sample x1 up to xn. You're going to take them to the power k, and you're going to calculate the average. And that gives you an empirical estimate of this Kate moment. The theoretical moment, well, we can get that from our appendix, right? So we can try to figure that out from the given distribution. That would be the theoretical Kate moment in my distribution. Okay. So what are we going to do now? Well, a method of moments estimate of theta would then be a matter of writing down the P equations. And where is the P coming from? That's the dimension of my parameter vector. So that's the number of unknown parameters that I need to work on. And what I'm going to write down is I'm going to say, okay, the first moment theoretically equal to empirical first moment, second moment theoretically equal to empirical moment, and so on. And I'm going to use these P equations to solve for the unknown P parameters in my distribution, right? And this produces an estimator that has, of course, the same first P row moments as the data. It produces a model that has the same first P row moments as the data. So let's do that with an example. So here I'm going to use my dataset B. So remember, dataset B were, I guess, 20 losses on the workers' compensation product. These losses were ranging from values, what was it, 27 up to 15,743. If I want to calibrate the exponential, the exponential distribution has only one parameter. So what I'm then going to do is I'm going to put the empirical first moment equal to the theoretical first moment and solve for the unknown parameters. I guess that's on the next sheet. So for the exponential distribution, you would say my empirical first moment, that's 1400 something. How did I get that? By summing my claims dividing by 20. That's 1400 something. And in the exponential distribution, with density 1 over theta exponential of minus x divided by theta, we can know from the appendix in Klugman that the mean is this parameter theta, right? So this gives me then the moment estimator for my unknown parameter theta. It's the 1400 something. So for the exponential distribution, single parameter, so only one equation I need to work with. If I move on to the gamma distribution, then I know there are two parameters. And again, I take my appendix from the Klugman book. I look at the expression for the mean of the distribution. If I'm working with a gamma with parameters alpha and theta, that mean is alpha times theta. The empirical mean is 1400 something. The second raw moment for the gamma can be expressed as follows. And the empirical second moment, I can square all the losses in my sample, sum them together, divide by 20, and I get this 13 million something. So what do I have now? I've got two equations, I've got two unknowns, so I can find the empirical estimate, the moment estimate for alpha and the moment estimate for theta. That's how it goes, right? And now you can say, well, this is moment estimation. So the disadvantage is here that this will only give us a point estimate, and we do not have all the machinery and all the theoretical nice properties of the alternative technique, maximum likelihood. So maximum likelihood is to be preferred because of its theoretical properties and all the machinery that comes with it. But we do often need these moment estimates to get a first feeling about what are sensible values for our parameters. And like here, I know that for the alpha, I should go with 1 over 5 approximately. And if I look at the theta, I know that I should have a value of 7,800 or something. Yeah, so that gives me good information, which is often helpful if I need to initialize my numerical routines for maximum likelihood estimation. So keep that in mind as an important takeaway. We also have that for the Pareto. So it's again a matter of looking up the first and the second moment, theoretically, putting it equal to the first and the second moment empirically, and solving for the unknown alpha and theta. And that will initialize the parameters in the Pareto distribution. Okay, so that's what I wanted to say about moment estimation. I particularly know that the econometricians will sometimes do this, or will be quite familiar with this, is then to say a few words about maximum likelihood estimation. So what can we do with the maximum likelihood estimation? Then we're going to put it here in a quite general way. Yeah. So what can we do here with the maximum likelihood? We're going to put it in a general way. We're going to look at n events, denoted here in an abstract way with A1 up to AN. So AJ is whatever was observed for observation J. Now this may look very strange, but the reason why we put it like that in this particular book is to cover all these possible data sets that we introduced before. And sometimes we have an actual observation. Sometimes we have a right-censored observation. Sometimes we have grouped data where we only know I've got that many observations over this kind of interval, etc. So it is in order to be able to capture all these different settings that we're going to work here with the notation with the events, so that the event can be an interval, but can also be one specific observation, etc. That's the next bullet, right? So it can be a single point, it can also be an interval. When is it an interval? In case of group data, but also in case of censoring. Think about my picture earlier on. If the loss is right censored at a certain value, let's say 5,000 euro, then this A would be the interval from 5,000 to plus infinity, right? Because that's the whole range of possible values that my loss ultimately can take, because I know that if it's right censored at 5,000, it will be at least as large as this 5,000. So the event AJ results from observing the random variable xj. We're going to assume that x1 up to xn all have some distribution depending on a certain parameter vector theta, and that these random variables are independent from each other. That's what we're going to do here in order to be able to write down the likelihood. Okay, so what is our likelihood then? The likelihood is a function of the unknown parameter vector theta, and we construct this function by saying what we're going to multiply is the probability that xj belongs to the interval aj, given the unknown parameters theta. We're going to take the product over all j. And we're going to look, that's my likelihood function, and we're going to look for that value of the parameter vector theta, which maximizes the likelihood function. Okay. So a few extra words on that. Why do we write the product? That's because of the reason of, because we made this assumption of independence. So we say because of the independence assumption, the joint likelihood, the joint distribution, the joint probability reduces to the product of the marginal probabilities. Yeah, that's because of this independence assumption. And the likelihood function then gives us kind of the probability of observing the sample results given a particular parameter value for theta. And so the maximum likelihood estimate of theta is then that value of the parameter vector that produces the model under which the actual observed sample or the actual observed outcomes are most likely to be observed. So once again, the maximum likelihood estimate, it's that value of the parameter vector, theta, which is going to produce the model under which the actual observations, the x's as we observe them, are most likely to be observed. So it's that vector of theta that's going to create the largest value here for this joint likelihood. And the samples, the x's, they are of course observed, so there is nothing that I can change. Now, if there is no truncation, if there is no censoring, and the value of each observation is recorded in full, then my likelihood becomes the product of the probability density function of xj, or the probability function in case xj is a discrete random variable. Then I just need to take this product. And then to optimize, to maximize, I'll often switch to the log likelihood. So then instead of working with a product, I'm going to work with a sum, right? The sum of the log likelihood contributions. Okay. So that's if you're facing individual data which are fully observed. So the title here specifies the scenario. So this is if I'm working with complete and individual data. But what if I'm working with group data, right? So with group data, the only thing I know is how many observations do I have in a certain interval. So I know that I have nj observations in the interval cj minus 1 to cj. So what I can then write for my event aj is that it's capturing, or we're going to express it as the probability that my random variable takes a value in this interval, right? So this is what we work with. This is my likelihood function. And what you see here now is the contribution of those nj observations in the interval between cj minus 1 and cj. How do I get that contribution? Well, then I look up under the proposed model, what is the probability to observe an outcome between cj minus 1 and cj? And I can write that as a difference of the CDFs evaluated in cj and cj minus 1. And then I take this probability to the power nj, because I observed nj values, nj observations in this interval between cj minus 1 and cj. And then the only thing I need to do is I need to take the product over all the intervals that I consider in my data set. If I take the log of the likelihood, the product becomes a sum. The thing to the power nj becomes nj times the logarithm of the contribution over here. So this would be the strategy that we apply if we're facing grouped data. And it still fits within this general approach that we took, because we started with this event aj. And the event aj, it's here about taking value between certain boundaries, in this case, cj minus 1 and cj. And then one of the last things I want to discuss is what happens if we have truncated and censored data. So with censored data, we're going to use the same reasoning as before. So if you look at right censoring, that creates an interval running from the censoring point to plus infinity. So what we need to put in our likelihood then is the probability under the proposed parametric model to observe an outcome that is at least as large as the observed value, right? But if I have data below the censoring point, so if I observe the loss in full, then I don't need to go to the distribution function term. I don't need to go to the interval term. Then I'll just go with a density function term. So then I'll just plug in the density function I'm working with observed in this fully observed loss. That's the difference here. And what if you have truncated data? So with truncated data, we're going to use conditional probabilities in the likelihood, because we know that we can only observe this particular outcome, given that the outcome, given that we are above a certain threshold. So that will be called, or that will be captured with conditional probabilities in the likelihood. So we're going to illustrate that a little bit on given data to make sure that it becomes a bit more clear, right? So if we look at data set B, yeah, and what we're going to do is we're going to do an intervention on this data set B, and we're going to assume that losses would be censored at the value 250. So that means whenever I had a loss that is 250 or larger, I would put it equal to 250, right? So if you go back to data set B, that means that the first 7 losses are fully observed, but then the other 13 losses, the only thing we know about them is that they will be censored, right censored at value 250. So how do we write the likelihood again? So what we know for the uncensored losses, so the first 7 losses, we observe them in full because they are below the 250. So for them, we just plug in the density of the exponential, evaluate it in the actually observed loss. So 27 up to 243. What you see here, each term is the PDF of my exponential, evaluated in that particular value of the loss. I put that all together, I get something like this. Then we have the final 13 terms, which are censored. So in that case, my interval, my set AJ, is the interval from 250 to plus infinity, because that's the only thing I know for those losses, that they will take a value above 250, but I don't know how much exactly above 250. So what I'm going to plug in my likelihood is the probability under the assumed exponential model to see a value above 250. So I'm going to work here with the survival function of my exponential with parameter theta, and I'm going to evaluate that survival function in 250. So that's what I get over here, and I get that 13 times because each of those last 13 losses is going to be right censored at the value of 250. So if I put it all together, I get a likelihood like this, which I want to optimize over the unknown parameter theta. So what can I do? I can switch to the log likelihood. I can take the derivative with respect to theta, put it equal to 0, and solve for the unknown value of theta. So that's what you see here. We switch to the log likelihood, we take the derivative, put it equal to 0, and solve for the unknown theta. Yeah, so this would be my MLE, my maximum likelihood estimate, in case I would pretend as if in dataset B, the last 13 losses were subject to right censoring at a value of 250. Questions? Does that work?